Hello, this is the final exam practice test. I'm going to be making a four-part video series just like I did for the midterm, covering about 7 questions per video. So we're going to start off with example number 1, which says solve this log equation. So when you're solving a log equation, the first thing you need to notice is whether or not every term in the equation has a log or not. Since there is a 2 here that is not connected to any log by multiplication at all, this is the type where we're going to get all logs on one side, and then we're going to use the definition of a log to turn this into an exponential equation. So this one's already pretty standard and set up for us. It's already got the log isolated on this side. So we use our conversion that says 5 to the second power equals x squared plus 9. Then we would work out 5 squared, which is 25, equals x squared plus 9. Subtract over the 25 to see if we can factor this. So that's going to be x squared minus 16. That is factorable. That would factor into x plus 4 and x minus 4. If we set each of those equal to 0, we get a negative 4 for the first factor and a positive 4 for the second factor. Now, with logarithms, you can't just say that any answer you get always works unless you check. The argument, which is the part that's in the parentheses, has to be greater than 0. So x squared plus 9 has to be greater than 0 by definition of what a log is. So if we plug in negative 4 squared plus 9, that would be 16 plus 9. That's definitely greater than 0. If we plug in positive 4 and add to 9, that would again be 16 plus 9, which is greater than 0. So both solutions work, so we would write it as negative 4 comma 4. All right, let's look at the next one. This is us converting something that is written as one big log into the expanded form, which means sum or differences. This is just giving you kind of the domain of this problem, even though we're not going to be doing anything with that. So when you're dealing with expanding a log or breaking it back apart, the first thing you want to take note of is if there's a fraction, that means there's division. So with logarithms, we have a fact that says if there's division between two parts in an argument, then you can separate that using the same log base and make it the top log's argument. So that's x to the 11th minus the bottom of that fraction. So let's log 2, x minus 7. And then if you had multiplication, you would split that up into addition, but we don't. You cannot split adding or subtracting up, but you can pull powers to the front as a coefficient. So this would be 11. I'm going to write my log as a cursive so it doesn't look like 111. So log 2 of x minus log 2 of x minus 7. And that's as far as we can go with that, so that's what we would write in this blank. Okay, so now we're going to move on to number 3. Sorry, my annotations are not deleting. I guess because I saved them. Let's see. Let's clear the screen. There we go. So let's move on to number 3. Sorry, I'm just getting used to using the annotations for Zoom. It's a little different, so we're just going to keep trying to move on. Number 3 says, what will a $90,000 house cost 5 years from now if the price appreciation for homes over that period averages 5% compounded annually? So anytime you're compounding and you're not compounding continuously, you're using the formula A equals P parentheses 1 plus R over N to the NT, where A is the future value, P is the present value, R is your rate as a decimal, N is the number of times you compound it in a single year, and T is the number of years. So it looks like we have a $90,000 house now. So it's going to be 90,000 is our present value. Our rate is 0.05 since it's 5%. We're compounding annually. That means once a year. Also put that here because n shows up twice, and then we're doing this for 5 years. So we want to get out our calculator, and you'll want to type all of this in at the same time without hitting clear or enter, otherwise you won't get a accurate rounding. So 90,000 times parentheses 1 plus 0.05 divided by 1, close parentheses. And I always multiply my exponent together in my head or on another calculator because I want to type it in just directly. So 1 times 5 is 5. So this is 114,865, and if we round to nearest cent, like they said in the directions, 34 cents. So 114,865.34. Okay. Moving on to number 4. This is graphing a quadratic by talking about whether it opens up or down, finding its vertex, axis of symmetry, and any intercepts. And then determine the domain and range of the function and where it's increasing and where it's decreasing. So if your leading coefficient is positive, then your graph is going to open up. The coordinates of the vertex are found by doing, if you're in standard form, which is what this is ax squared plus bx plus c, you find your coordinates of your vertex by first doing the first part of the quadratic formula. So x equals negative b over 2a. So that's going to be negative 1, because that's the b coefficient, divided by 2 times a, which is 2. So this is positive 1/4. So we would go ahead and write that as the first part of our ordered pair. But we need the y coordinate as well. So you have to go back and plug this value into your function. So we're doing f of 1/4. So 2 times 1/4 squared minus 1/4 plus 7. 1/4 squared would be 1/16 minus 1/4 plus 7. So I'm just working this out. 2 and 16 reduce. This is 1/8. I'm going to go ahead and get a common denominator. Multiply this by 2 over 2, so that'd be 2/8. This 7 over 1 can also be multiplied by 8 over 8, so that would be 56 over 8. So that would be negative 1 plus 56 is 55 over 8. So that's my y coordinate part of the vertex. The axis of symmetry is a vertical line, so x equals, and it goes through your vertex, so x equals 1/4. And it does say to type this as an equation, so if you put just 1/4, it's going to count it wrong. To find your intercepts, the y-intercept is very easy. It depends on which ones they're asking. It looks like we can write them all in one line together. So if you want to find your y-intercept, you plug in 0 into your function for x. So what that ends up being is you just get the constant at the end. So it's 7. So that would be 0, 7, and then we're going to separate that because I'm sure there's some x-intercepts. To find your x-intercepts, you set the entire function equal to 0 and you try to solve. So we could try to see if this is done by factor by grouping, but I don't think it is, so we're going to use quadratic formula. So x equals negative b, so that'd be negative 1, plus or minus square root, and then we have b squared minus 4ac all over 2a. That is 1 plus or minus the square root of 1 minus 56 over 4. Now, this is not going to give us any intercepts because this is the square root of negative 55. That is imaginary. So you can't have imaginary numbers on a real axis. So this is the only one, so we could actually erase that comma. So there's just the y-intercept. Now it says for us to choose the correct graph. Well, our graph should open up, so these two are out automatically. And our graph should cross at 0, 7. This one's crossing, I believe it's this first one that's going to work. 1, 2, 3, 4, 5, 6, 7. Yep. The other one crosses too high on the y-axis. So that's our perfect graph. Now, your domain of any polynomial is always negative infinity to infinity. Polynomials, unless they are restricted by like a set of directions that says don't use x is less than 1 or something like that, polynomials are always all real numbers. The range is determined by what's your lowest point of your graph, or your highest point, depending on if you're going up or down with your graph. So this is a lowest point of that vertex y value, which was 55 over 8. Everything else has a higher y value. So 55 over 8 up to positive infinity is the range, the y values that are being used. The function increases from the vertex to the right of that. So that would be, and when we use increasing, decreasing, we don't usually use bracket for that because it's an idea of increasing involves more than one point. So the vertex, and when you're talking about increasing and decreasing, you always want to do it in reference to your x values. So our vertex was at 1/4. So from 1/4 to positive infinity, that's from this point to the right, we look like we're going up a roller coaster. And from negative infinity to 1/4, it looks like we're going down the roller coaster. And then this was just from that number 1 part. Okay, let's talk about number 5. This is another log equation, and this time we have logs in everything. So when you have logs on every term, as long as you get one log on each side, which we already have set up, then as their bases match, then the arguments have to match as well. So we have to solve this by setting the argument of the left side equal to the argument of the right side. So x equals 3. Now we still need to check it. 3 plus 2 needs to be greater than 0, which it is, and this also is greater than 0 by itself. So the only solution is positive 3. Okay, so this one right here is solving a polynomial inequality. Anytime we're solving one of those, we want to get everything on one side and 0 on the other. So our first step would be to subtract over that 12, and then we'll have greater than 0. Now, the way I teach this in the face-to-face courses is slightly probably different than what you guys did, but I find that graphing these sometimes or looking at a graph is not always intuitive for students. So if you can factor this, which we'll give you one that's factorable, this would be x plus 4 and x minus 3. Both of these numbers multiplied together are going to determine the sign of this overall left side. So if we look at just the places where those two guys equal 0, and you want to look from left to right, so smaller one would be negative 4 and positive 3. So we're going to break our number line into the intervals negative infinity to negative 4, and negative 4 to 3, and 3 to infinity. Now if this had an equal to, I'd be putting brackets on my numbers, but not my infinities. So we pick a test value because whatever sign we get when we multiply these two guys together, it's either going to multiply to a positive or a negative. So I'm going to pick a test value of negative 5 since that's in this interval, 0 is in this interval, and positive 5 is in this interval. If you plug that into the problem, you can tell if this has the correct sign we want. This would be negative 1 times negative 8, which is positive 8, which is greater than 0. So this first region is true. If we plug in 0, we see that we get 4 times negative 3, which is negative 12. Is that greater than 0? No. So this region's out. And then if we plug in 5 plus 4, 5 minus 3, that would be 9 times 2, that's 18, and that is greater than 0 like we want. This region's good. So my solution set, since there's two separate intervals that worked, is negative infinity to negative 4 union, because that means or, parentheses 3 to infinity. So that's just a nice way to just do these really quick. You factor, you find all of your things that make these equal 0, place them in order from least to greatest, put up your number line intervals, and then pick test values and see if the statement is true or false. All right, and then this is the last one for the first part of this series. So the function f of x equals x squared minus 4 when x is greater than or equal to 0 is 1 to 1. Find the inverse of f and check the answer. Find the domain and range of both f and the inverse, and then graph them and the line y equals x on the same coordinate axis, because you're supposed to reflect over this line if you've got the correct inverse. So to find your inverse, I'm going to have to work this over here. Think about it being y equals x squared minus 4. The first thing you have to realize is that in an inverse, you are swapping your domain and range, which means you're swapping x and y. So we're going to rewrite this as x equals y squared minus 4. Then you would resolve for y. So I would add 4 over to get the y by itself. And then I have to take a square root. Now normally if we're taking a square root, we have to write plus or minus. but only one of these can be correct. So that's why they gave you this hint right here. When you're dealing with the original function, this is the domain. That will be the range of the inverse function. So our y has to be greater than or equal to 0 based on what we learned about how inverse relationships swap domain and range. So that means we would just choose the plus case. So my inverse is just going to be the square root of x plus 4. The domain of the original function is already given in the problem because they stated it right after it. It's x is greater than or equal to 0. And then the range of f has to do with this square root problem, or sorry, not the square root problem. It has to do with the function's height and where we're at. So if you look, and in fact, it's easier if you just find both domains first. So let's talk about the domain of this guy. When you're dealing with the square root, you set the inside part greater than or equal to 0. You want to keep that positive or 0. You don't want imaginary numbers. So that would be x is greater than or equal to -4. So that means this guy has that exact same answer, but for its range, because remember they swapped the domain and range in an inverse. So y needs to be greater than or equal to -4, so it would be this option. And then remember, we're just flip-flopping. So x is going to be greater than or equal to -4 when we're dealing with the inverse. And y is greater than or equal to 0 for the inverse. So notice domain and ranges swap. All right, that's the end of part 1 of the video. I will be working on part 2 next.